just to recall what we did last time, we will need a few definitions. So let's start with where we left off. So we learned Bayes' rule last time. So it was basically the following, which is probability that you have x conditioned on y. This conditional probability is simply probability of x and y, the joint probability divided by probability of y. Yeah. That's basically straight from the definition. We also did probability of y comma x, which is basically equal to probability of x comma y divided by probability of x. And so you can put them together and you basically get probability of x given y is the joint probability, but you can use this expansion for joint probability. And you basically get probability of y given x times probability of x divided by probability of y. Okay, so this is basically what we did last time, and this was what we called as Bayes' rule. And the entire lecture today, we're basically just going to be working with this. So it's kind of important to make sure you get to know this, which is probability x given y is y given x times probability of x divided by probability of y. Okay. So in case you weren't here, this is kind of important. Okay. Okay. So how are we going to use this? What we're going to try to do is try to make a prediction based on some set of observations that you have. Okay. And that is basically central to pretty much any sort of machine learning method that you can come up with, which is you have a task, which is some prediction, and what you have is a set of observations, and you are basically trying to figure out how to make that prediction given those observations. Okay, does that make sense? So very, very concretely, what this means is we're going to find the probability of a prediction. So I'm going to call it class for now, but this can be any prediction given you see a series of observations. Okay. So this can be pretty much anything. So this could be, my task today can be given a series of observations that I have around the room, I want to predict something. Okay. So the task could simply be, my observations can be, all of you guys report your heights, all of you guys report maybe your weights, all of you guys tell me your shoe sizes, and then I need to predict whether you are a male or a female. Okay. So that's basically what we're trying to predict, which is whether you're a male or a female given a set of observations that I have. Okay. And it turns out that many of the times this probability, computing this itself is hard, and that's basically where this comes in handy. So we're going to expand this and say that to do this prediction, instead we're going to say this is probability of observations given class. Okay. Times probability of class. Okay, that's just taking Bayes' rule and just applying it to the problem. Good so far? Okay. And note that this is central to pretty much any kind of learning method that you would want. There's not anything specific, right? Any prediction you want to make, you have a set of observations, you want to make prediction. This is kind of what you want to maximize. Okay. Now let's say that I have a bunch of different outcomes possible. Class here takes those values. It's either male or female, for instance. a more real world example can be the set of observations that I'm seeing is my session. Okay, so I'm going through my session logs and I have a series of observations. So these observations can be how long has this user been on the site, right? Which is the page that the user browsed on the last? Does the user have something on the cart? Those could be all the observations, and the class can be whether this person is going to convert or not. Okay, so the class is basically two classes. You either predict he is going to not convert or predict he or she is going to convert. Similar setting, you have a series of observations. You want to predict if the person is going to bounce or not. So you see a session. Those are your observations. Prediction is two classes here. Is he going to bounce? Is he not going to bounce? Okay. So there are three important terminologies. It's just good to know. This, you might hear people toss these terminologies around. So it's good to know. So this term here, people call it the posterior. Okay, which is basically typically what you want. You're given a set of observations. You're trying to make a prediction. This is what people call as a likelihood. Okay, which is if you were a bouncing user, what's the chance you could be seeing what you saw? It's the flip side of what we wanted to predict. Okay, and these two guys here are what people call as priors. Okay, priors are basically things that you don't have any observations and you're basically asking for a probability. It's like asking how many people, if I pick a random person in this room, what's the probability it's a male? I'm not telling you my height, I'm not telling you my shoe size, I'm giving you no information. Blindly I'm asking what's the probability you're male. I'm blindly asking what's the probability the user is a bouncing user. No, I'm not giving you any more information. So those are called priors. These terms are likelihood, these terms are posterior. Generally posterior is what you want. Posterior is many times hard to compute, so you use the likelihood and the priors to compute the posterior. Okay, those are just terminologies. We won't really talk about those terms specifically. So what's the problem that we're trying to solve? We're trying to find the class that maximizes this probability. Correct? So there could be two classes. Is the person a bouncing person or not? You compute this probability for the bouncing person. You compute this probability for the non-bouncing person. Whichever is the higher probability is what you're going to predict this person is going to do. Okay? And the formal way of writing that is basically saying what we want is argmax of, I'm going to abuse notations a little bit. C belongs to class, probability of C given my observations. Okay, and this is going to be equal to probability of my observations. I'll show you. Given C, times probability of C. Okay, so this is one tricky step to follow, and it's important to make sure we follow this. So what's going on here? So I'm going to go over every possible class. Okay, and I'm trying to figure out what's the posterior, which is equivalent to figuring out for this specific class, what's the probability of seeing these observations given the class times the probability of the class itself. I'm losing the denominator here. And the reason I'm losing it is because this is constant over all classes. This doesn't even have the class term here. Make sense? So let's take a specific example. What's the probability the user is going to bounce given what we saw? Is the probability of what we saw given the user is going to bounce times probability of bounce divided by probability of what we saw. Okay. The flip side is going to be what's the probability user does not bounce given the observations, which is seeing the observations given user does not bounce, probability user does not bounce, divided by probability of observations. It's the same probability both sides. So we can lose that. Okay. This is what we want. This is like one tricky step. People good?
But at that point, we don't have a probability anymore, just a number.
Correct, that's true. So this argmax is true in the sense whatever class maximizes this also maximizes this. But you're no longer dealing with a probability because you lost the denominator. If you had the denominator, you can get a value between 0 and 1, but now this value could be bigger than 0 and 1. Okay? I'm just simplifying things. Good so far? And then we just have one last step, and then we're basically done. And it's probably better illustrated with a.
It will be.
Yeah.
No, I mean not bigger than 0 or 1. It will be less actually. I mean, we 0 to some range less than 100.
That's actually true. You're going to have probability of observations itself is going to be between 0 and 1. That's right. Okay, cool. So let's take a concrete example actually. And this is the example we're going to talk about for today, which is trying to take a text from a web page and trying to figure out which category it belongs to. Okay, so we're going to take product title, product description, and then figure out which top-level category it belongs to. So this is going to be taking categories like electrics, baking tools, cooking tools, cutlery, and trying to look at the words, and then taking just the words and trying to predict which category that they belong to. Okay, so the observation here is the text that we're looking at, and the class is the top-level category. Okay, so let's take that concrete example. So then, what we have now is basically argmax C belongs to a category, right? And we're going to maximize the probability of the category given my words. Okay. Okay, so far so good. And we're just going to use one more piece that we learned last time, which is independence, and specifically conditional independence. And what I'm going to do here is basically call this argmax over C. So this is the only other tricky step, which is product over all, let me call it words. In words, probability of Wi given C times probability of C. Okay. So what did we do here? So I'm looking at a bunch of text, okay, in a single category. So this could be cutlery, and we have a bunch of words on the page. Now, if the words on the page were all independent given the category, then I can take the probability of seeing all the words simultaneously and break it up into seeing the words independently. Okay. And last time we saw text on a page, and we saw which are the words that are independent and which are the words that are dependent. Like stainless steel was dependent on each other. If I told you that stainless occurs, with a very high probability steel occurs together with it. If I saw angelus occurred, with a very high probability loss occurs with the text. But this is a reasonable assumption in practice, especially for classification, which is we take the words, break it up into single words, assuming that they're independent. And so what we finally get is we find the class that maximizes the product over probability of all the words given the class times the probability of the class. Good? Okay. And the cool thing about this is the reason we started off with changing the posterior to likelihood, because these things are now fairly easy to compute. This is simply the category frequency, okay, which is if I took a page at random from the site, what's the chance it's a cutlery page? If I took a page completely at random from the site, what's the chance that it's an electrics page? That's it, which is just looking through the entire site, looking at the frequency of each of these categories. This is simply word frequency in a category. Okay, which is given that you are in an electrics, can you compute the table of all the word frequencies? Make sense? And that's it. We are actually done. So the cool thing about this is you wanted to maximize this. This is really what formally you ever want to in some ways maximize, which is the probability of this class given an observation. You have a bunch of observations. Which class is the one that's most probable given my set of observations? And this is equal to this. And these two terms are equal to each other. The only assumption we are ever making in this entire thing is that the words are independent. Okay? But the amazing thing about this is if the words are independent, and in general, if the features are independent, then doing this literally just maximizes this. That is like no difference. So that's why it's like so elegant, but at the same time so powerful. And this is not just for text classification. This is true with any machine learning problem you want to solve. Okay? If I want to predict if a person is going to bounce or not, if my set of observations are independent, which is, what's the last category the person looked at, what's the whether the person has something on the cart or not, when was the last time the person visited the site, how long has he spent on the site, and so on. If all of them are independent, this is it. You just take each feature, each observation, and you basically say, what's the probability of seeing that observation if he's a bouncing user? What's the probability of seeing it if it's not bouncing? Multiply it with the prior. Figure out which one maximizes this product of probabilities, and you're done. Okay? And intuitively, all that this thing is doing is biasing it towards bigger classes. Because if you forget this is just word frequencies. Literally just word frequency for every category, and just multiplying the word frequency of every category. Right? But when in doubt, this term kind of biases it towards the bigger categories. Because if I don't have information, if the entire text on my page is saying Los Angeles, what do you want to predict? You want to predict the one that is biggest in size. Maybe electrics is 90% of the site. So this term kind of biases it towards that. Make sense so far? If this doesn't make sense, then we're in trouble because we're going to go code this up. So the cool thing about this is, the reason I wanted to code this up is we can start with a very formal, clear definition of what we want to do, come up with just one assumption to something that is very realistic, and we can actually implement this in practice and observe it. And I've done this implementation twice in production level infrastructures, and they actually work pretty well. And it's cool. It's very simple. You just need to compute the category frequencies. You just need to compute the word frequencies, and you're basically done. Okay.
There is an implementation trick, right?
What do you mean?
And if you kind of like multiply all these values, they're all from 0 to 1. So if there are lots of words, the value you will get is very small. So that's why you can take logarithms and kind of like turn it into sums, and so that you.
Cool. So actually, that's a good point. So what the implementation will tell us is we can actually run through a real world scenario, because the thing is, what you face in reality is not always the same as what we saw here. I mean, you will run into implementation hurdles. Besides bugs, we'll likely run into Python and so on. But we'll likely also run into other issues, like instability issues that he's pointing out. We'll likely run into some other problems that we don't anticipate. So that is obviously a gap between what's in theory and what's in practice. But just doing this end-to-end will tell you, if you were to go and implement this for anything in the future, whether it's bounce rate prediction, whether it's conversion prediction, whether it's classifying pages, classifying search queries, for instance, you want to know if it's a web search query, image search query, anything you want to do, how do we do it? Okay. So we're going to do 2 steps. We're going to take a subset of the pages. We're going to learn from those pages. We're going to take about a good fraction of the pages, figure out what the category frequency, figure out what the word frequency is within each category, and then we're going to use that information on the remaining portion of the site to predict the category given the text. Okay, good so far? And needless to say, I'm going to need all the help because I'm sure I'm going to have bugs. But we can try this. It might be a failed experiment, but at least it's an experiment nevertheless. Okay, so this is what I have. So the get bigrams is something we went over last time. I'm not going to talk about it right now, but if we have time, we can get to it. But the only other file that I have here is this Earl Crumb title body shuff. So let's look at the file. Can everyone read the file? Okay. So the Earl is the Earl. We can ignore it for now. That's the category. Okay. So it's electrics is a category. Tabletop and bar is a category. Bakeware is a category. Okay. And the next column is basically the title. So in this case, Queso Pro 1800 induction burner is the product title. Obviously, it's an electrics page. That's the body, and that's it. Okay, so that's the file. Makes sense? We have URL title, URL, top level category, title, and body. Okay. Cool. So, yeah, feel free to ask me questions. So that's about 5,200 products we're looking at. Right? So let's try to take 4,231 of it and put that into a training sample, and then take the bottom 1,000 and put that into testing. So we're not going to use the testing one to learn, and we're just going to use the training one to learn. So this is it. I mean, we literally are going to start with an empty Python, empty Emacs editor, and type the code out. So let's give it a shot. So okay, I would like a 2 tab, but I'm not going to try to change Emacs definitions right now. Okay, so let's get the training file. We're going to need sys.argv1, and let's look at the testing file, sys.argv2. And the two things that we want is the prior and the likelihood from reading the training file, right? So I'm going to read the training file, pass in the name of the file, and what I want are the priors and the likelihood. Okay. Once we get that, we are going to go through the testing file. This is probably not the best abstraction, but we're going to try to do it fast. And classify each line. Okay. Got to classify the line, pass in the priors, pass in the likelihood. Thank you. And if this classification equals line of 0, 1, then we're going to say num correct plus equals 1. We start with num correct equals 0. And we are basically going to, and then we are done. So we're basically going to say print classified %t correctly out of %t for an accuracy of %f %num correct len of lines float num correct over len of lines. Okay. Sorry, what was it?
The comma after this string should be removed.
Oh, good point, yes. I'm mixing up C++. All right, good. Okay. This is why I think debugging is going to be so much easier than if I were to write by myself. All right, so I think we're good. So the only things we need is to read the training file, read training file, file name, and we are going to split by tabs, and that's going to be parts. And we need a prior and we need a likelihood. So the priors is going to be just a counter for the set of all the category sizes, and the likelihood is going to be a counter for each category. Okay, it's a word count for each category. And then we're going to import this, import counter and defaulted. Okay, and we have the category in first column, so we're just going to do that, which is parts of 1 plus equals 1. That's it. That's the priors, right? It's kind of simple. And we're going to go over each word in the title, and then we're just going to increment likelihood of parts of 1 of word plus equals 1, right? And I think we're actually done. What was it, Chahan?
Just title for body?
Yeah, let's start with title. Actually, it'll be good to see how the accuracy kind of improves as well. So tokenize of text is just breaking it up into break up text into words. Okay, and this is going to be just literally just breaking it up. So we need an RE. Okay. So we are close. So that, yeah.
Priors of the titles?
Huh?
The priors of the titles?
No, the priors are basically, oh, good point. So this should be likelihood of parts of 2. 0, 1, 2. Is that, so that's what you mean, right? No, this is right, this is right. No, so the first column is basically the URL.
Yes.
The second column is the category.
Okay.
And the third column is the title. Okay, cool. So,
Tokenize return.
oh, good. Thank you. Okay, so let's now do that, and then let's implement classify. I think that's what we're done. So what we're going to do for classify is, let me start with a simple one. Okay, so I'm just going to do, and these are always good to know, I'm just going to return a random category. Okay, and then we're just going to measure a performance, okay, and how it does. So it serves as a good baseline for how these methods will perform compared to others. So this will basically, return a random category. Okay, so I would do priors of keys and categories, and then we're going to return categories of random times len of categories. I need to cast it into int. I think we're done. Oh, good point. There's a reading testing file. Good point. Okay, I'm just going to hack it up. Okay, file name. You could probably reuse the code, but I'm just going to hack it up. So I'm going to do open file name, read lines. But I think I need parts of it. So I'm going to do line strip dot split for line in. That's why Python is great. And I think we're done. Do people agree? Let's give it a all right, so let me know if you can't read it. So we're going to do classifier, Earl Crumb title chef train, Earl Crumb title chef test, 8.6% accuracy. Okay, it is. Let's first make sure it's right. I mean, I have some suspicions. So let's try to maybe first just let me print the priors, so we get a sense for if this guy is doing the right thing. So those are the priors. Okay, so this should match up with F12 of.
Well, there are 12 categories, and random means you get 1 of 12 correct. So each one, 6
is roughly right. Yeah. Okay. So this anyway, I'm just looking at the priors, right? So these are the priors, right? So this just tells you the sizes for each. How many pages are there in my training in each one of these categories, right? So there are 802 tabletop and bar, 528 food, 487 cooks, tools, and so on. And we just picked a random category, and we have an accuracy of, I guess, 8.6, 9.2, whatever. It's random, so it is going to change every time you run it. Kind of make sense? Okay. Actually, I wanted to record this. It's too bad we didn't start. But let's record this now. Okay. So what I thought was we could do this, which is method accuracy, and let's call it Bayesian classifier. What did we do? Random 9.2%. All right. Cool. So let's do something better than random. But let's take a look at the likelihood as well. I just want to make sure we are not making any mistakes. So let's go through just printing the likelihood. I just want to take a look at it. Likelihood. So that's roughly the likelihood, which is for every category. So in bakeware, the most common word is pan, which makes perfect sense, right? Sonoma and Williams don't really make sense, but hopefully the word frequencies in all the other categories are similar for these words, so they will just sort of cancel out. So let's see if I can find another one. So Williams Sonoma home is basically anything that you can put in your home, which is kind of a really hard category to look at, right? Because everything is kind of home stuff. Agrarian is probably easy. It's everything to do with garden. There's kit, garden on top, planter on top. I guess there's something to do with chickens. So those are all good. Cooking tools is all good. And those kind of roughly make sense. I think that's probably not a bug. Cool. So let's keep this classify function, classify random, and start a new one, which is a very important function in these methods almost always, which is to predict the maximum prior. And I'll say why that's very important. So let's say that I'm trying to predict. So what's the domain that we're dealing with? How hard is this problem? Let's say I'm trying to predict whether a user is going to convert or not. I can very easily get a 99% accuracy. Okay, I'm just going to predict every single user is not converting. That gives me a 99% accuracy. My method is like incredibly good, but not really, right? I mean, that's kind of a crappy method. So what's the domain that we're dealing with? Are we dealing with this 99 to 100 range that you're trying to optimize? Or are you dealing with this 10 to 100% range that you're trying to optimize? If that were one category here, that was a killer category, okay, that was Williams Sonoma home, 90% of the products are there, then I can get a 90% accuracy just by predicting everything as Williams Sonoma homes. So it's important to know what these are. So what we're going to do is do the max of the priors. I don't think that works, but we can fix it. And then we can say biggest whatever category. And I am actually, that's it, right? I'm just going to return that. Okay. And this is going to be return the biggest category. Okay. These are the sorts of issues I did not want to run into, but let's try to make sure we can do this. Okay. C of C is my counter, and do you guys see what I'm doing wrong? That should be fine, right? Why is my thing out of range?
But you did not say the value using the X.
Yeah, because that's the key. That's the key, yeah, so it's CX.
Bracket X.
No, it's not a function declaration. It's not that often. It's fine.
It should be fine, right?
Because apparently you're just getting the key. You're not getting the value.
No, x of 0 is the key. So that makes
No,
sense.
X0 is the first letter of the key. X1 is the second letter of the key, which you don't have.
I see, okay. I want what? Huh.
I'm sitting at an
Okay,
Srinath, instead of X1, why don't you go
like that.
no, bracket, C of X,
X.
square bracket?
Yes.
Oh, x is, why is x? Okay, I'm only getting the key on the x. Okay,
Yeah, you're only
good,
getting
okay.
the, yeah.
Okay, good, all right. Thanks.
It's the inverse, right?
Huh? No, this is fine, this is fine. So I just need max of return max of priors gamma key equals x equals cfx. Okay, cool.
Not
prior.
Thank you. All right, cool. Okay, so classify max prior. Okay, so we just do max prior, and I think we're done. So let's just print it. Okay, I think we can figure this out. Okay, so let me remove those prints. Okay. Cool. So about 18.7%, which let's take a look at this. So the biggest guy here is tabletop and bar, which is about 8,000, about 800 out of about 4,000. So that kind of makes sense, right? So then we get an 18.7% accuracy. Okay, let's do this. So max prior is 18.7%. Okay, so we're doing good on time. So even though I got stuck a little bit there. Cool. All right, so now for the real deal, right? Let's go for the main thing. Classify Bayesian, and then we have lines, priors, likelihood, and return the class that maximizes the posterior. Okay. Okay. So what we're going to do is line of 1, 2 is my title. I want to tokenize my title, and then go over all the words for word in that. I need my I have to go over all the classes, which is priors.keys, and then I'm going to go over all my words, and then this guy is going to have the priors of C. Note that I did not divide by the number in the priors. That's okay, because all the terms have the same denominator. Okay. But what we did not do also is in the likelihood I did not divide, and there the denominator depends on the class. So we need to get that guy here. So we need to get likelihood of C, right? And I need to make sure that I sum these values. Okay, does that make sense? Because we need the denominator for the likelihood, because this n is going to be different for each class. And let me make sure these guys are in floats. Okay, and then we just multiply. So we just multiply p equals p times for each word. We just multiply the probability of the words. So we just go likelihood of the class and the word Okay, and then we are done. And then here we just say if P is greater than max class of 0, then my max class equals P comma C. Okay, and then I'm going to set my max class outside. Max class equals minus 1e6 and then empty. Okay, and then we're just going to return max class of 1.
You haven't used the denominator.
I haven't what?
Use the denominator.
Use what?
P by M.
Oh, good. Thank you. Good. I think that kind of works. Hopefully everything gets cast into floating point. And all right, you guys think it works? No? All right, let's see.
That's my prior.
All right, let's see.
Well, Seth can always change his definition of words to be anything greater than 60%.
Yeah, 54%.
Yeah, 54% it kind of seems bad. All right, so this is where theory, so this is, we're done with the theory, right? So it's good that I got this done on time. So now let's see what we can do from here on, okay? So this is where it's all from here on, it's practice, okay? So this is typical of what happens, so this is it. And then, okay, so let's take a look at what's going on.
If you predict according to the distribution, you should be get close to 50% anyway, right? Just predict according to the likelihood.
It's multi-class.
No, right, it's not, I mean, with likelihood is okay, but if you just use the prior, you cannot get this. You cannot get 50, because if it's just 2 classes, you will get 50%. But these are like, 13 classes or 15 classes or whatever, right? So you will only get like 10%. That's why we did that baseline. This is the best you can do. 20% is the best you can do, or 18.7. So we are already in much better than something that's random. Okay, so now let's take a look at this, which is, this is another common problem that happens, which is, let's take a look at our guy here, which is this max class. Let's look at, man, Pradeep and I share the same, we have a history concatenating thing, but nevertheless, hopefully I don't. Lot of zeros, like Chauhan points out. And the lot of zeros happens because if you look at that equation there, right, we have the probability of words of I given the class. Now let's say I encounter a word I've never seen before. Those probabilities will become zeros. A single word in my title that I see that I've never seen in training will wipe out all the other probabilities. Make sense? And I'm guessing, like Chauhan said, that's why we have these zeros. Okay, we can fix that. This is where it's a hack, huh?
If you increase the training to, let's say, 5,000 acres, right?
Correct.
And you tested
Those will go down. Yeah.
So is it, I mean, how does the, I mean, what's the theory beyond how it improves?
So, I mean, this will improve, but at the same time, in practice, for sure, there will be words that you don't see in because let's say you have like an item ID, you have like a new product name, right? I mean, I'm sure all these have unique product names, right? So I'm sure there will be long enough tail that it's hard to do this in general. But with 5,000, but you're absolutely right. These will go down, which is why the theory it's fine, it's solid.
Your simple code, you didn't actually. So when you read that, as you are reading each line from the test data, you can improve on the training also, right? From that, you're not doing that yet.
Absolutely. So what we can do then is that's absolutely right, and that's very crucial to do that. But it's in itself a hard thing to do. So what we can do is next time we'll go through exactly that, and we'll do it. So right now though, let me push this to the limit. Okay. So here like we saw that this guy likelihood is becoming zeros, right? So we can do a max here between. I never want this to go to 0, so let's do 1e minus 6. So 1 in a million basically, and I don't need to import anything for max, I think. And classifier of pi. That's pretty good now. Okay, so you're looking at 86% accuracy. Okay, 0 fix. You're looking at 86, and this is basically where sort of theory meets practice kind of thing. Dude, I have no idea, dude. but so firstly, here itself you can play around, right? I mean, is 1e minus 6 the correct number? Is it 1e minus 2? Is it 1e minus 9? We can play around. That sucks, but let's try that. It's about basic. So okay, so let's keep that. Okay, so let's keep that aside. We never actually looked at body, so let's do that immediately. So let's say I took, this is fairly easy to add. So let's say I did my tokenized parts of 2. I just need to add parts of 3 there, and then I go to my tokenize there, and then I add line of 3 there. I think we are done, right? Unless I'm mistaken, I think we're done.
You treat body and title the same.
Exactly. So I treat body and title as the same. So let's run this, and then let's split them up and see what changes. Because if we split them up, we are going to get a lot more information than if we keep them together. Like you pointed out, that's precisely right. So let's do both, because this is quick checks to do both. Yeah, it took longer. Clearly, you can see that. 89.8. Okay. So at some point in time, obviously, you're going to start tapering out. But 89 point, what was it? 8. Okay, so let's do what Hai suggested, which is split them up. So all that I need is then def tokenize title body and so what we're going to do is we're just going to return I'm sure somebody can write a better version of that. Plus b for b in tokenized body, but we have very little time. Okay, so I think that probably works. So we can do tokenize title body and that separately, and then tokenize title body separately. Okay.
What about stemming?
Okay, actually, let's wait for a second, because so stemming can definitely help. But I see the 0.0 here. Okay, so this is sort of theory meets practice. This is exactly what we're dealing with here. Right? I see the 0.0, which should never happen because we have the 1e minus 9 there. So let's take this opportunity to go back to what Salim was talking about, which is let's try to take those guys out, because the reason we're getting zeros is because these probabilities are ending up being very small. So we could probably fix it by changing it to 1e minus 6, but let's take this chance to do what he was suggesting, which is take the log there and take the log there, and we need a math, I think, and let's try that out. I think the denominator is inside the log though.
So you can remove it out.
Yeah, it's fine. Either way is fine, I guess. Fine. I think it's the. No, let me leave it there. I think it's okay. Yep.
Some math is not long.
Ooh, awesome. So we did what? Zero fix. So let's separate the two out actually. So I wish I could. Okay, let's separate the two out. So this was a, let's call this, okay, let's separate the two out. So which is, let's try to get just the log without the tokenized title, okay? Because we did this tokenized title body. So let's try to split them up.
What change was the title body change?
We split the titles and bodies separately so that you have even more. So if you have a lot of data, this is going to help.
No, it's not, right? Because you're not treating title and body any differently. Even if you split them up, they're still two set of lists treated exactly the same.
There is no kind of like weight scheme, right?
There is no what?
The only way it will improve is if you weigh the title more than the body.
No, that also can improve by itself, so we can have a separate field there. But what this tells you is, let's say the title distribution was different from the body distribution, theoretically. Okay, in the end, it might be the exact same distribution, in which case it will have the exact same accuracy. But let's say the title distribution is different from the body distribution. This will have an opportunity to capture that.
No, it won't, right? Because
Except for there is no separate weight. But let's say that if a certain word was present in the title, then it immediately tells you what the category is. In the previous case, it will get washed out with the body. But now you have the title colon the word separately there.
Well,
Okay, let's.
for likelihood, aren't you, for when you split the title and body separately, in your reading training file, when you, after you tokenize title and body separately, they're all going into the same likelihood.
No.
No?
It will be, a term will be title colon word one, title colon.
Oh, I see.
she has prepared the title and body,
So that they don't overlap. Yeah, exactly. So let's look at this, so which is my tokenize. Let's look at my tokenize function back again, which is there and there. So then going back, oh, the only problem is I think the log kind of got triggered because of this change. But let's check this out anyway. Let's see if this does anything. Okay. All right, so this was basically title, body, and log space. Okay, so that gave us 90.8%. So you're getting up in the
What was
90s.
the previous one? It was different.
Yeah, so previous one was title and body separate, right? So let's go back to that.
No, 91.3.
Yeah, well, that's what I'm doing right now. So it was title and body separate. Right now I put it back together because I think we fixed the log issue first. So now I'm going to get back to the title and body being separate. And tokenize. And this was, I guess, 91.3, you know that, but I forgot the number. Yeah. So this was Bayesian, zero fix, title, body, separate, and then log space, 91.3%. Okay. I think we might be close to getting kicked out. But let me say one more thing, which is, firstly, this is getting up there, right? We are now into the 90s, right? If I were to do a random prediction, we would have been in 20s, okay? We would have been in 18.7. So we've gone from there all the way to like a 91% accuracy. And we could push it further. We can look at what got misclassified. It's probably a good exercise, right?
Can you do a quick like weighting even the title like 1.5?
I mean, those would. I mean, we have to think through carefully. I mean, we can obviously hack it up so that we can just multiply the probabilities with some random constants and so on. But
No, let's just try it. Just multiply the title with like 2 or 1 just to see if it works.
Okay. We have to be careful, right? Because we have to do it both in training.
So you need this body kind of like shows the different kind of like accuracy will start with. Then we'll know that okay, there are two different kind of combinations.
Okay, so I mean, okay, this is like, I mean, there are some hacks that I guess is okay, but okay, if just to give this a shot, we can give this a shot just in testing if you want, but exactly. So if word what starts with like that, right? Title, then we're going to do, let's do whatever. So my max of 1e minus 9, and what do you want, 2 times that? Okay.
So it's not like the Horionic with maths.
No, you need to, otherwise it goes 0.
The log zero.
Is negative infinity. Hey! Good job, guys.
All right.
Let me say one more thing that I wanted to say.
So now you're getting into the law of diminishing.
Right. So let me say one more thing, which is the following, which is we did this tokenize thing, right? What we can do is, so we did this tokenize and we broke it up into single words, right? I probably don't want to get into it and then get into a mess, but what we can instead do is tokenize based on the bigrams that we built in last lecture, okay? I don't know if you guys remember, but so we did, this was, I didn't show the code, but this is roughly the kind of code that we used, which is we went through the data file, found like the unigram frequencies, found the bigram frequencies, and then selected the pair of words where the joint probability was much higher than the product of the marginal probability, product of the individual probabilities, okay? So P of x comma y was significantly higher than P of x times P of y. In this case, it's 100x, but then we say that those two are bigrams, okay? So stainless steel was a bigram, Los Angeles was a bigram, and so on. And so then we have this list of bigrams that we looked at last time. What you can do is you can build a tokenizer that tokenizes based on that. So as you go through the string, you pick all the unigrams, but then if the next pair of words is present as a bigram, you take that together, okay? And the reason you want to do that is if they're not independent, so this is the sort of math it's fairly easy to see. If they're not independent, then you will be multiplying the probabilities twice instead of multiplying them once.
Which lower overall.
Correct. So let's say Los Angeles always occurs together, right? Theoretically, you should multiply it once, but instead now we'll be multiplying it twice within that category, okay? And that could change things significantly. It'll actually, in some ways, also increase the probability because in comparison to others, right? So Los Angeles, let's say, only occurs in cutlery, okay? I'm just making it up. Then you will multiply the loss for the cutlery, Angeles for the cutlery. Both of them will have defined values. And then you'll multiply 1e minus 9 times 1e minus 9 on this some other category, okay? Which is going to hurt that much worse than otherwise. So if it occurs together, you want to use this kind of tokenizer to break it up into independent chunks and then multiply the independent chunks rather than using just breaking up into words and just multiplying it. We could measure that probability as well and try to see how it does, but I think we're actually fairly good on time, although we got stuck there once with that lambda function.
The probability that a computer is mutual information, EXY.
Yeah, it's a thing called point-wise mutual information. But that's exactly right. But we need, but it's just a test for independence. Yeah. Okay. Any questions?
Can you do the quick step test?
Stemming is going to be stemming is going to be tricky. I need Porter stemmer and stuff.
Remove ING and remove ER.
It's not, the cool thing is it's not going to hurt you so much, right? Because those words will occur in all the other categories as well. It is good to remove it, obviously. There is no doubt about it. But
but then you got in title, right?
no, but all of them are going to have the same. All of them are going to have. Just because of noise, some will have more than the others, and therefore you might end up hurting them more, or helping them more.
No, I mean stemming or stop words.
I think he's talking about stop words now.
He's talking about stemming.
Yeah.
I mean, you can do both, but
Stop words doesn't hurt you at all. They're stop words.
I mean, just because of noise, it could hurt you. Theoretically, stemming also doesn't hurt you if you have enough training data, right? But the issue is
variations of the stems will occur.
correct. But the issue is just because of noise, you have some variations occurring, some variations not occurring. Just because of noise, you have overrepresentation of stop words on one side as opposed to the other side. But if you know it's never going to impact it, then it's better that you remove it rather than have that noise play into the classification.
Maybe you should talk a little bit about cross-validation or different size training tests and things.
Yeah, so we can do some of that next time. So let me talk high level, right? So what are some of the issues here? Which is, let's say that, firstly, there is differences in a training set and testing set sizes. Let's say that there is this issue that you are dealing with an offline case where you want to just learn these parameters, but when do you overfit the data, right? And so we haven't talked about any of that, which is how do you, when do you know that you overtrained your data and you're actually doing bad? So what you can do is you can do things like you just do leave one out cross-validation, where you just leave one data point out, use all the others, and you sort of train it so that the prediction accuracy is highest. Does that make sense? The other problem, which we could talk about next time, is what happens if your training set is biased. In the sense, now I was able to estimate my priors easily because I just counted the set of pages that were in different categories. But let's say that this is this is big. This is the web. Okay, you have 1 billion pages, and now you want to do the exact same experiment. You no longer can count the set of pages that's in electrics. Okay, so what you then do is you go say, well, I have all these billion documents. I'm just going to have a manual QA to do QA of 100 documents a piece for electrics, 100 documents a piece for cooking tools, agrarian, food. And they're just going to give you the word counts. So then you get the likelihood you can compute. But prior is even prior because you don't know which one is overrepresented. How do you deal with that, right? And that we can talk about next time, which is sort of what I think Praveen was pointing out as well, which is how do you take the testing data and kind of use it for training, okay? So we can talk about a little bit of that, which is you do this accuracy, you do this classification, and then you have an output, and how do you use that output back? Yeah, so there are a lot of associated problems.
That's cheating though, right?
No. So you can do a lot of things like that. So so think about even the following. Let's say I did not even give you a classification. Okay, I didn't even tell you these categories. Here are the web pages on this site. Can you somehow figure out what are the clusters that's there? How do you compute that likelihood without any training data? Okay, that's not cheating at all now, because you're literally saying come up with a system where you automatically come up even with the labels and iterate the learning process, right? So we can talk about it next time, and how with little to no training data you can still kind of do something. So there are lots of associated problems here.
Goes from the supervised learning to unsupervised learning.
Exactly. Cool. So we can hack everything up offline, but I think 1 hour is a good time to stop also for the video. All right.